DKW Physics. I'm Mr. McConnelly, and today we're going to figure out the coefficient of friction between this cardboard box filled with bricks, a box of bricks, and the tabletop, a resin tabletop. Now, coefficient, just to remind you, is how slippery two surfaces are against one another. And it's just a relative comparison. So a block of wood on sandpaper has a higher coefficient than a set of shoes on a sheet of ice. Okay? That would have a lower coefficient, so when two things slide across each other easily, they have a low coefficient. Alright, so we're faced with this question, or this problem. How do I figure out the coefficient with a box of bricks on the tabletop? And the first thing I'm going to do is I'm going to get the mass of the box of bricks. And this is for some of the people that may be viewing the video. This brick may look familiar to some people viewing the video. That means nothing to most people. Now, this box of bricks, of course I have a scale that's going to read in kilograms because that's what we work with in the international system. This box of bricks actually masses out at 8 kilograms. 8 kilograms. So we'll jot that down, students jot that down. And I'm going to pull this box of bricks with a spring scale that reads in newtons. So as I pull this box of bricks, I'll actually be able to read the spring scale and get a certain number of newtons. But if we can just, for a moment, pan to the front, we're going to do a little bit of figuring here on the board before we come back and actually do the demonstration. So, how do we go about this? Well, the first thing we're always going to do is we're always going to take and figure out our picture. So we have a box of bricks on a tabletop, and we got to label the forces. So give me one of the forces, Joe.
Force of gravity.
Force of gravity, point straight down. Tricia, another one.
Normal force.
Normal force. Up. Another one, Ashley.
Force of friction.
Force of friction. Now, which way do you want the box to be moving?
To right.
So we're going to move to the right, so which way does friction go?
Left.
Left, okay. So, friction. And then, obviously, we're pulling it, and usually we call that applied. So the next step is, Cheyenne, what do we usually do at this point when we have all our forces? Where do we go with the problem?
You add them all up and set them equal to F net.
Okay, so F net equals all of them added together. So we got the normal one, and the force of gravity, and the applied force, and the frictional force. And what do we know that we can always do, Dana, when we have this scenario with this sort of picture? Are there two that can cancel? Well, of course, because they are equal and opposite, we can get rid of them right from the beginning. So we've kind of simplified it down already. The net force is equal to the applied force plus the force of friction. Now at this point, Stephanie, what are we going to remind ourselves that F net is the same as?
Mass times acceleration.
Okay. And Kaylee? What is FF the same as?
Mu times Fn.
Mu times Fn, right. And where am I actually going to get this applied force from, Kyra?
It's going to be how much you're pulling on the box.
Yeah, it's going to be how much you're pulling on the box. So this is me pulling, and we'll read that off the scale. All right. But Lucas, I have a little bit of trouble finding Fn, so what am I going to set that equal to help myself out?
You can set it to the force of gravity, which is just mass times gravity.
So he's thinking, off to the side here, he's thinking Fn is equal to the force of gravity, but the force of gravity is mass times gravity. So, okay, he's going to have a new equation then that says mass times acceleration equals this one that I don't know that I'm going to come up with once I pull the spring scale, mu, and then mg. I substitute the mg in for the Fn. All right, so all I got to do is pull it. But, Chase, I got a problem. And the problem is, how am I going to get that acceleration?
You could just keep pulling at the same speed so the acceleration is 0.
Well, that's a good thought. So, if I make the acceleration a 0, like I pull it at a constant speed, then I won't have to worry about finding it at all. In fact, what it'll do is it'll take the problem and it'll say, okay, this whole side is now 0. That'll be the force that I pull with. Remember, I'm trying to find coefficients, so now it's like a piece of cake if I can pull at a constant speed. So let's go ahead and do that and see what we get for a number. So back over here with our box of bricks. Our box of bricks, remember, has a mass of 8 kilograms. And we're going to pull here, and I'm going to have to pull it for a ways because it's going to be hard for me to try to get the number consistent. Well, it was ranging a little bit, but I'm going to go with 19 newtons. 19 newtons. So we have 19 newtons to pull an 8 kilogram box. And I think that's all we'll need to finish this problem off. So let's see here. We got the left-hand side of the equation is still 0, because I pulled it at a constant speed. The question mark one was me pulling, and I said that was 19, didn't I? And we got mu, that's the one we're trying to find. We got the mass of the box, which was 8 kilograms. And of course, our friend acceleration of gravity is 9.81 meters per second squared, and it's a negative, because it's always a negative because it's pointing down. Well, how do we solve the problem? First, actually, we
Subtract the 19.
over to the other side, very good. Leaving ourselves with mu, 8 kilograms, and negative 9.81. And then at this point, it's just a little bit of calculator work. Notice there's a negative on both sides, so they'll cancel out, leaving us with a positive mu value, and looks like Lucas has it.
0.24.
0.24. Anyone second that opinion in the back? Okay, Joe's got a second on that. 0.24. So that means our box has a coefficient of friction between that cardboard box and the plastic resin surface of the table of 0.24. Now, just to talk about this, previously, before the video started, we did the same experiment, but we did it with a much heavier box. And when we did it with a box that actually weighed 13 kilograms, had more bricks in it, the mu value came out to be 0.31. Now, 0.31 is close to 0.24. I mean, they're not the same, but should they be the same? And the answer is yes, because it still is cardboard on a resin tabletop. No matter if you put a lot of mass in it or a little mass in it, it's still the same two surfaces. So when we do the problem, irregardless of how much mass you put in the box, the numbers like the applied me pulling, the applied force, and the mass are going to change, but in the end, it should all come out in the wash, and you should still get the same mu value. We were close. Now, one more thing I want to do before we cut off the video is I want to go to our physics reference table and look at some approximate coefficients of friction. And first of all, was this a static situation or a kinetic situation? Kinetic, because we were moving it, okay? We weren't trying to get it moving, we were already moving and we were just keeping it moving. So we're in a kinetic situation, and as we scan down through here, are there any numbers that come close? Well, the closest one I see to 0.24 that's listed on the reference table is wood on wood. So if you have a piece of wood being dragged across a piece of wood, it should come out to about 0.3. Can you see in your mind that that's kind of similar? Cardboard on a plastic top might be a similar number to wood on wood. In comparison, the much higher numbers are things like rubber on asphalt, and the much lower numbers are things like Teflon on Teflon or rubber on ice. So, for today, I hope you wrapped your mind a little bit more around the ideas of coefficients of friction, physics.